Hello, in this class let's discuss coherent states. We saw that the expectation values for x and p in energy eigenstates do not oscillate like a classical oscillator. Because for any state, for any energy eigenstate, the expectation value of x and the expectation value of p was found to be 0, even for large values of n. But if the state in which we calculate the expectation value is a superposition of energy eigengates, then we saw that the expectation value of x actually oscillates with a classical frequency omega. And this is consistent with the Ehrenfest's theorem that we saw earlier. We may now ask, how can we construct a superposition of energy eigenstates that most closely imitates the classical oscillator? A classical oscillator is a particle in a harmonic oscillator potential. We know that it just bounces back and forth. And now we are asking if there are quantum mechanical states that behave in a similar manner. In the language of wave functions, we are looking for a wave packet that bounces back and forth without spreading in shape. We have seen that wave packets or wave functions have a tendency to spread out in space as the system evolves in time. Even if we start with a wave function corresponding to a localized particle, after some time the wave function may spread out over larger regions of space. But here we are looking for a wave packet that will not change its shape. We shall see that these kinds of wave packets actually exist, and such quantum states that exhibit classical behavior have a special name. They are called coherent states. It turns out that the eigenkets of the annihilation operator A actually satisfy the requirements for a coherent state. So let's start by writing down an eigenvalue equation for the operator A and then examine the properties of these eigenkets. We shall write the eigenvalue equation like this. A acting on ket lambda is equal to lambda multiplying ket lambda. Here, ket lambda is the eigenket of operator A corresponding to the eigenvalue lambda. Now, since A is not Hermitian, these eigenvalues can be complex. Let's now examine the properties of these eigenkets of operator A. First, let's look at the expansion of these coherent states in the energy eigenkets and also the related probability distribution. As we already know, ket lambda can be expanded in this basis, in the basis formed by the eigenkets of Hamiltonian. Okay, so we write it as sum over n equal to 0 to infinity f of n ket n, where f of n are the expansion coefficients. That is, f of n is actually equal to the projection of ket lambda along ket n. From the probability postulate, we know that modulus f of n square gives the probability for a measurement of energy En. Now, if you look at the distribution of these probabilities with respect to n, we'll see that it's a Poisson type of distribution about some mean value n bar. This distribution can be shown as to be modulus f of n square is equal to n bar raised to the power of n divided by n factorial exponential minus n bar, where n bar is the mean value. Let me explain how we get this. We can get to the nature of this probability distribution by looking at these expansion coefficients. We have to start with the only thing that we know about ket lambda. That is, ket lambda is an eigenket of the annihilation operator. So let's look at the effect of the annihilation operator on ket lambda. For this, we can write ket lambda as f of 0 ket 0, which is the n equal to 0 term in the summation, plus sum over n equal to 1 to infinity f of n ket n. We have separated out the n equal to 0 term. Now, A acting on ket lambda becomes f of 0, A acting on ket 0 plus sum over n equal to 1 to infinity f of n, A acting on ket n. Here we have used the fact that f of n commutes with the annihilation operator because f of n are numbers. So the annihilation operator just passes right through these numbers and acts on these energy eigenkets. All right. Now we know that A acting on ket 0 is equal to 0. All right. We have seen that A annihilates the ground state. So we are left with A acting on ket lambda is equal to sum over n equal to 1 to infinity f of n A acting on ket n. We know the action of A on ket n. We have already seen that this is equal to square root of n multiplying ket n minus 1. We can use that here. So this becomes sum over n equal to 1 to infinity f of n square root of n get n minus 1. That's the step that we have here. Now we can redefine the summation index for convenience. We can introduce a new summation index. M is equal to n minus 1. This means that n would be equal to m plus 1. All right, wherever n appears here, you can write it as m plus 1. And when n is equal to 1, right, if n is equal to 1, the corresponding value for m is n minus 1, that is 1 minus 1, which is equal to 0. So in terms of this new summation index, the summation will be from 0, right, because corresponding to n equal to 1, the value for m is equal to 0. Okay, so with this new summation index, this becomes sum over m equal to 0 to infinity, and f of n becomes f of m plus 1, right, according to this thing. And then this becomes square root of m plus 1, and get n minus 1 is written as get m. Now m is a dummy index here, so it's okay if you use n here. We can write this also as sum over n equal to 0 to infinity f of n plus 1 square root of n plus 1 get n. We use the same index n here because from the beginning we represented the energy eigengets as get n. Right? It's okay if you write it as get m here, but just for the sake of familiarity, we shall use the index n itself. Okay. Here is the state A get lambda expanded in the energy eigengets. Now by definition, A acting on get lambda is equal to lambda multiplying get lambda. Using this for A acting on get lambda, this eigenvalue equation becomes sum over n equal to 0 to infinity f of n plus 1 square root of n plus 1 get n, which is A acting on get lambda, is equal to lambda multiplying sum over n equal to 0 to infinity f of n get n, right? And this is get lambda. Now we can equate the expansion coefficients corresponding to get n on both sides. So we get f of n plus 1 square root of n plus 1 is equal to lambda f of n, or f of n plus 1 is equal to lambda divided by square root of n plus 1 multiplying f of n. So this expression gives us the n plus 1th expansion coefficient given the nth expansion coefficient. We have f of n plus 1 in terms of f of n. Let's put n equal to 0 in here, and then this becomes f of 1 is equal to lambda divided by square root of 1 f of 0. Alright. Similarly, if you put n equal to 2 in here, n equal to 1 in here, we get f of 2 is equal to lambda divided by root 2 f of 1. Now we can substitute for f of 1 from here. So we get f of 2 is equal to lambda divided by root 2, lambda divided by root 1 f of 0. Okay. We have just used this expression for f of 1 here. Now we see the trend. In general, we can write f of n is equal to lambda raised to n divided by square root of n factorial multiplying f of 0. So this gives us any expansion coefficient in terms of f of 0. If you determine f of 0, then we have all the expansion coefficients. Is there any relation that we can use to determine f of 0? Indeed, there is the normalization condition. The normalization condition says that sum over n equal to 0 to infinity modulus f of n squared is equal to 1. This is just the requirement that the probabilities over all the possibilities must add up to 1. Now we substitute for f of n from here, which we already found out. Alright. So modulus f of n squared, this is equal to f of n multiplying f of n complex conjugated. Now using this expression, we can write modulus f of n squared as lambda raised to n divided by square root of n factorial f of 0 multiplying lambda raised to n star, the complex conjugated, divided by square root of n factorial f of 0 complex conjugated. The n in the denominator here does not need a complex conjugate because these are real numbers, right? These were eigenvalues of Hermitian operators, whereas the lambda here is an eigenvalue of a non-Hermitian operator. So it can be complex. That's why we need a complex conjugate here. Now we can make use of the fact that lambda raised to n complex conjugated is equal to lambda complex conjugated raised to the power of n. This can be proved by mathematical induction. If you already don't know this, I leave that proof as an exercise for you. Here, let's just make use of this. So this expression becomes lambda raised to n, lambda star raised to n divided by square root of n factorial multiplying square root of n factorial gives n factorial, and f of 0 multiplying f of 0 complex conjugated gives modulus of f of 0 squared. Now this can be written as lambda lambda star raised to a power of n divided by n factorial modulus f of 0 squared. And what is lambda multiplying its own complex conjugate? This is modulus of lambda squared. Okay, so this expression becomes, let me write it here, this becomes modulus lambda squared raised to n divided by n factorial modulus f of 0 squared. This is modulus f of n squared. What we need is sum over n equal to 0 to infinity modulus f of n squared equal to 1. So a normalization condition is now written as sum over n equal to 0 to infinity modulus lambda raised to 2n divided by n factorial modulus f of 0 squared is equal to 1. Alright. Now this f of 0, modulus of f of 0 squared can be pulled out of this summation, and we can write this as modulus f of 0 squared sum over n equal to 0 to infinity. We write this modulus lambda square whole raised to n divided by n factorial. Alright, and this summation has to be equal to 1 according to the normalization condition. Now, if you look at this, you see that here we have the Taylor series expansion of an exponential, because we know that exponential of x, for example, is written as sum over n equal to 0 to infinity x raised to n divided by n factorial. Here, in place of x, we have a modulus lambda squared. So this means that we can write this as modulus f of 0 squared. This is exponential modulus lambda squared. Okay, this is equal to 1. So a normalization condition now becomes modulus f of 0 squared multiplying exponential modulus lambda square is equal to 1. Okay. From here we see that modulus f of 0 squared is equal to exponential minus modulus of lambda squared, and this means that f of 0 is equal to exponential minus modulus of lambda squared divided by 2. We are just taking the square root on both sides. Earlier we had f of n in terms of f of 0. Here we have f of 0 in terms of the eigenvalue of the annihilation operator. We had f of n is equal to lambda raised to n divided by square root of n factorial multiplying f of 0. And we found that f of 0 is equal to exponential minus modulus lambda square divided by 2. So we just substitute this f of 0 in here, and we get f of n is equal to lambda raised to n divided by square root of n factorial exponential minus modulus lambda square divided by 2. These are the expansion coefficients. Let's find the corresponding probabilities or the probability distribution. We just take the modulus square of f of n. So modulus square of f of n gives modulus of lambda raised to 2n divided by n factorial. The square root of n factorial squared gives n factorial. And this exponential squared gives exponential minus modulus of lambda squared. Now you see that this modulus of lambda square is real because it's a modulus square of a complex number. Let's write this as mu. So let's put mu equal to modulus lambda square, and the probability distribution becomes mu raised to n divided by n factorial exponential of minus mu. And this is the Poisson distribution. The only thing left to show is that this mu here is actually the average value of n. So let's do that next. The mean value of n, denoted as n bar, we already know is sum over n multiplying the probability for n. This weighted sum is what we call the mean value of n. And we found this probability distribution to be mu raised to n divided by n factorial exponential minus mu. The first term in this sum corresponding to n equal to 0 is 0, because here the first term will become 0. So 0 multiplying anything is 0. So first term in the summation is 0. So we have 0 plus sum over n equal to 1 to infinity n mu raised to n divided by n factorial exponential minus mu. Now this n divided by n factorial is 1 divided by n minus 1 factorial, right? So we can write this as sum over n equal to 1 to infinity mu raised to n divided by n minus 1 factorial exponential of minus mu. We can pull out exponential minus mu from this summation. We can also pull out one of the mu from here. All right. So we pull out exponential minus mu multiplying mu. And here we are left with mu raised to n minus 1. Okay, because one of the mu we have pulled out. So this becomes exponential minus mu sum over n equal to 0 to n equal to 1 to infinity mu raised to n minus 1 divided by n minus 1 factorial. Now again, we redefined the summation index. Okay, just as before, we just put n minus 1 is equal to m. So again, the summation becomes from m equal to 0 to infinity, and we get n bar is equal to exponential minus mu multiplying mu. That these terms are here, and this summation becomes from m equal to 0 to infinity mu raised to m divided by m factorial. And what is this? This is the Taylor series expansion for exponential mu. Okay, so we get n bar equal to exponential minus mu multiplying exponential minus mu, and exponential minus mu multiplying exponential mu is equal to 1, and we see that n bar is equal to mu. So the mu appearing here in this probability distribution is actually the average or the mean value of n. So putting mu equal to n bar, we get modulus f of n squared is equal to n bar raised to n divided by n factorial exponential of minus n bar. Okay, we have seen that the distribution of modulus f of n square with respect to n is of the Poisson type about some mean value n bar. The next important property is that a coherent state can also be defined as the ground state translated by a finite amount. To show this, again we start by writing ket lambda, right, expanded in the energy eigenkets. Now we substitute for f of n, which we already found. F of n is equal to lambda raised to n divided by square root of n factorial exponential minus modulus lambda square divided by 2. Now we can also make use of this expression ket n is equal to a dagger raised to n divided by square root of n factorial acting on ket 0. This is something that we saw in one of our previous classes. We can substitute for ket n with this here, all right, and this expression becomes exponential minus modulus lambda square divided by 2 sum over n lambda raised to n divided by square root of n factorial a dagger raised to n divided by square root of n factorial acting on ket 0. Now we can combine these two terms to lambda a dagger raised to n, and these terms in the denominator get multiplied to n factorial. Okay, so this is ket lambda now. Again, what we have here, this is again the Taylor series expansion for an exponential. All right, this is the Taylor series expansion for exponential lambda a dagger. So ket lambda is now written as exponential minus modulus lambda square divided by 2 multiplying exponential lambda a dagger acting on ket 0. All right. Now we can show that the ground state translated by a finite amount gives a coherent state written in this form. Let's now see how a coherent state can be obtained by translating the ground state by a finite distance. It's easy to show this if we use what's called as the BCH formula or the Baker-Campbell-Hausdorff formula. We shall not prove the formula here, we'll just make use of this. So this formula allows us to write exponential of x multiplied by exponential of y as a single exponential. Okay, so according to this, exponential of x multiplying exponential of y is exponential of x plus y plus half commutator of x and y plus 1 divided by 12 commutator of x with the commutator of x and y minus 1 divided by 12 the commutator of y with the commutator of x and y plus etc. Okay, clearly this is not a simple formula to remember. But there is an important special case to this formula which makes it useful in many situations. There are situations where the commutator of x and y commutes with x and y. Okay, for example, this happens when the commutator of x and y is proportional to the identity operator. For example, if you remember, the commutator of x and p is IH bar. All right, this is proportional to the identity operator, which means that the commutator of x with x and p is equal to the commutator of x with IH bar, which is equal to 0. All right, because we know that this is not an operator. There's an identity operator here, but any operator commutes with the identity operator, so this is 0. Similarly, the commutator of p with the commutator of x and p is also 0. In such cases, all these higher terms are going to be 0. So we'll need to use only these three terms in here. In that case, it's very simple to use this formula. Now you see that if x commutes with y, then exponential of x multiplying exponential of y is simply exponential of x plus y. This is something that we always use when we are working with commuting quantities like numbers. But when dealing with operators that do not commute, we have to be careful. All right. So if the commutator of x and y commutes with both x and y, then we can write exponential of x multiplied by exponential of y is equal to exponential of x plus y plus half commutator of x and y. Okay. It may be helpful to memorize this special case of the BCH formula. This is going to be very useful for you. You can convince yourself about this special case of the BCH formula by working out problem 3.29 in the textbook Introduction to Quantum Mechanics by Griffiths. It's actually Introduction to Quantum Mechanics, 3rd edition by Griffiths and Schroeter. So work on this problem and convince yourself that this special case, at least this special case of the BCH formula, is correct. The textbook is Introduction to Quantum Mechanics, 3rd edition by Griffiths and Schroeter. I think that's correct. Here we shall just use this formula, exponential x multiplying exponential of y is equal to exponential of x plus y plus half exponential of x and y. Now, if the commutator of x and y commutes with x and y, we can separate this. All right, we can write this as exponential of x plus y, the first term here, multiplying exponential half of commutator of x and y. Again, remember, we can do this only if this term commutes with this term. From here, we can write exponential of x plus y is equal to exponential of x multiplied by exponential of y multiplying exponential of minus half commutator of x and y. This is the form of the BCH formula that we are going to use now. Now let's apply the finite translation operator to the ground state. This is something that we have seen in the first chapter. Exponential minus IPL divided by h bar is the translation operator corresponding to a finite translation equal to L. P here is the momentum operator, the generator of space translations, and we can substitute P is equal to I square root of mh bar omega divided by 2 A dagger minus A. Substituting for P in this form we get this is equal to, or the translated ground state can be written as exponential square root of m omega divided by 2 h bar L A dagger minus square root of m omega divided by 2 h bar L A, and this whole thing acting on ket 0. And in these steps we have just done some rearrangements. Okay, nothing serious. So this is the state obtained by translating the ground state by a finite distance L. This is of the form exponential of x plus y with x equal to square root of m omega divided by 2 h bar L A dagger and y is equal to square root of m omega divided by 2 h bar L A. There's also a minus sign here. Okay. Now we can simplify this using the BCH formula. But we need to use only the special case because if you look at the commutator of x and y, okay, it involves the commutator of A dagger and A. We know that the commutator of A and A dagger is equal to 1. All right, which means that the commutator of A with the commutator of A and A dagger is 0. Similarly, the commutator of A dagger with the commutator of A and A dagger is also 0. This means that we can use the special case of the BCH formula. All right. So the thing here is that X, we can find the commutator of X and Y, but the commutator of X and Y here commutes with the commutes with X, and the commutator of X and Y commutes with operator Y also. Okay, so we can use the simplified BCH formula. Applying the BCH formula, we get exponential of X, exponential of Y, all right, multiplying exponential of minus half commutator of X and Y. All right, let's evaluate the commutator of X and Y. This is X and this is Y. So the commutator of X and Y is equal to, there are some constants here, we can pull that out of the commutator and they multiply to give m omega divided by 2 h bar. Okay, there's an L here and an L here, so we have an L square, right? And then the commutator of A dagger, then there's a minus sign here with the commutator of with minus A. Sorry, the commutator of A dagger with minus A. So this is equal to m omega divided by 2 h bar L square. We know that the commutator of A with A dagger is 1, which means that the commutator of A dagger with A is minus 1. But there's a minus here, so this commutator is also equal to 1. All right. So the commutator of X and Y here is m omega divided by 2 h bar multiplying L squared. So the translated ground state now becomes exponential of X, exponential of Y, exponential of minus m omega divided by 2 h bar L squared divided by 2 acting on ket 0. All right. Now there are no operators here, all right, except for the identity operator. So it commutes with all these operators here. We can pull it to this side. All right, this exponential minus m omega divided by 2 h bar L squared divided by 2 can be pulled out like this. Okay, and then here we'll have exponential of, let me just write that. Okay, we have got exponential of minus m omega divided by 4 h bar L square, which is this term. All right, and then we have exponential of square root of m omega divided by 2 h bar L A dagger acting on exponential of minus square root of m omega divided by 2 h bar L A acting on ket 0. Let's look at just this term. All right, so you notice that here this term is actually missing. I'll explain why this is missing. This is because exponential minus square root of m omega divided by 2 h bar LA acting on ket 0 is written as, we can make use of the Taylor series expansion. So this is the identity operator minus square root of m omega divided by 2 h bar LA, okay, plus etc. And in all these terms, you are going to have an A or the higher orders of A square, A cube, etc. And all these terms acting on ket 0 returns 0. So the only non-zero contribution from this Taylor series expansion is because of this identity operator acting on ket 0. All right, which means that exponential minus square root of m omega divided by 2 h bar LA acting on ket 0 is equal to ket 0 itself. Okay, so using that we write exponential, using that we get the translated ground state as this factor multiplying exponential square root of m omega divided by 2 h bar LA dagger acting on ket 0. All right. Now you remember that we wrote the coherent state in this form. Ket lambda is equal to exponential minus modulus lambda square divided by 2 exponential lambda A dagger acting on ket 0. What we have here is exactly of this form with lambda is equal to square root of m omega divided by 2 h bar multiplying L. So this indeed is a coherent state, as we understand by comparing this to our previous expression for the coherent state with lambda is equal to square root of m omega divided by 2 h bar multiplying L. What we have seen is that the ground state translated by a finite amount gives a coherent state. Okay, or a coherent state can be obtained by translating the ground state by a finite distance. I hope this is clear. You really have to carry out these calculations by yourself for more practice. Okay. Let me repeat. We have shown that we can obtain a coherent state by translating the ground state by a finite distance. Let's now discuss the time evolution of a coherent state. It's easy to describe the time evolution of a state if you write it in terms of energy eigenkets, because we know that energy eigenkets just pick up a phase factor under time evolution, because if you have the state ket n, the energy eigenket ket n, we know that after some time this just becomes exponential minus IENT divided by h bar multiplying ket n. So the energy eigenkets just pick up a phase factor under time evolution. So it's easier to describe the time evolution of ket lambda if you write it in terms of the energy eigenkets. We can also use the expression for f of n, which was lambda raised to n divided by square root of n factorial exponential minus modulus lambda square divided by 2. So with that, we can write the coherent state at a later time t as sum over n f of n, which is lambda raised to n divided by square root of n factorial exponential minus modulus lambda square divided by 2 multiplying exponential minus IENT divided by h bar multiplying ket n. Now for harmonic oscillator, En is equal to n plus half h bar omega. Okay, so exponential minus IENT divided by h bar becomes exponential minus I divided by h bar. En is n plus half h bar omega, and there's also a t here. Okay, the h bar cancels and we get this is equal to exponential minus I n plus half omega t. So the state at a later time t, ket lambda of t now becomes sum over n equal to 0 to infinity. This is f of n at time t equal to 0 multiplying exponential minus I n plus half omega t multiplying ket n. Now this term can be written as this is exponential minus I n omega t, okay, multiplying exponential minus I by 2 omega t, okay, and this exponential minus I omega t divided by 2 can be pulled out, so we have written it here, and this exponential minus I n omega t, this term can be written as exponential minus I omega t raised to the power of n. We can combine this term with the lambda raised to n here and write this as lambda exponential minus I omega t raised to the power of n. Okay, divided by square root of n factorial. The exponential minus modulus lambda square divided by 2 is written as it is, and then we have ket n here. All right. Now, if you look at this, we see that here there is an exponential minus modulus lambda square divided by 2. We know that this also can be written as exponential minus modulus lambda e raised to minus I omega t square divided by 2. We can also write it like this because the modulus square of e raised to minus I omega t is just 1. Right? So you could as well put an e raised to minus I omega t in here along with this lambda. Alright, now let's compare this expression. Alright, this is the state at time t, get lambda of t. Let's compare this expression with the state at time t equal to 0, which is here. Alright, we see that there is this multiplicative factor exponential minus I omega t divided by 2. Other than that, what we have here is instead of lambda here, we have lambda exponential minus I omega t. Alright, instead of lambda here also we have lambda exponential minus I omega t but that modulus square just gives 1, so we haven't written it here. Okay, so the time evolved state is also exactly of this form with the eigenvalue. Right, here the lambda is the eigenvalue, but in place of eigenvalue we have lambda exponential minus I omega t. Alright, so we see that the eigenvalue lambda has evolved to lambda exponential minus I omega t. Right? Other than that, this state looks exactly like this. There's an extra multiplicative phase factor here. which does not change the eigenvalue equation, etc. So let's not worry about this term. Okay. Now what we see here is that the time evolved state is also a coherent state. All right, because it is still an eigenket operator A with eigenvalue lambda exponential minus I omega t. So initially it was an eigenket of operator A with eigenvalue lambda. Now it's an eigenket of operator A with eigenvalue lambda exponential minus I omega t. Okay, which means that the state has remained a coherent state. It's still a coherent state, right? It's still an eigenket of operator A. The only thing is that the eigenvalue has changed. So the time evolved state is also a coherent state. I hope this conclusion is clear. So apart from the overall phase factor exponential minus I omega t divided by 2, ket lambda of t is the same as ket lambda but with eigenvalue lambda of t is equal to exponential minus I omega t multiplying lambda. Let's now calculate the uncertainties for position and momentum operators in coherent states. And we are going to see that a coherent state satisfies the minimum uncertainty product relation at all times. That is, coherent states are minimum uncertainty states. To show this, we shall make use of this eigenvalue equation satisfied by the coherent states. The dual correspondence of this equation also is going to be useful. Okay, so the dual correspondence of this equation is bra, bra lambda a dagger is equal to bra lambda lambda star, where lambda star is the complex conjugate of lambda. We will also make use of the position and momentum operators written in terms of a and a dagger. Okay. The commutator relation is also going to be useful because we can write this as a dagger minus a dagger a is equal to 1, which means that a dagger can be written as 1 plus a dagger a. This is going to be useful because what we have is a relation like this. A acting on ket lambda is lambda multiplying ket lambda. Okay, and bra lambda a dagger is equal to bra lambda multiplying lambda star. We can use these relations only if A is acting to the right or if A dagger is acting to the left. And using this relation allows us to shift the order or change the order of A and A dagger. Alright. So if we have A dagger, we can write just 1 plus A dagger A. First, let's find the expectation value of x in a coherent state, which is bra lambda x ket lambda. We now substitute x equal to square root of h bar divided by 2 m omega a plus a dagger. Now this can be expanded as bra lambda a ket lambda plus bra lambda a dagger ket lambda. Now we can use the relation a acting on ket lambda is lambda multiplying ket lambda here, right? And bra lambda acted upon from the right by a dagger is equal to bra lambda lambda star. This can be used here. Okay, so this expression becomes, and this lambda can be pulled out of this scalar product because this is a number. Okay, so this becomes lambda multiplying bra lambda ket lambda plus lambda star multiplying bra lambda ket lambda. And we had already normalized the state ket lambda, which means that bra lambda ket lambda is equal to 1. All right. So the expectation value of x in this coherent state becomes square root of h bar divided by 2 m omega lambda plus lambda star. Now let's calculate the expectation value of x square, which is bra lambda x square ket lambda. Again, we substitute for x in terms of a and a dagger. Squaring that gives h bar divided by 2 m omega a square plus a dagger square plus a dagger plus a dagger a. All right. Now we know how to work with these terms because this can be, for this we can use a square acting on ket lambda, and for this we can use a dagger square acting on bra lambda. All right. This also we can work with because here we have got a acting on ket lambda and a dagger acting on bra lambda. But here we have a on the left and a dagger on the right, which is a little bit inconvenient. So we use the commutation relation to write this as 1 plus a dagger a. Now we can use the eigenvalue equations. All right. Before that, we can combine this A dagger A plus A dagger A to 2A dagger A. All right. So the expectation value for x square now becomes this. Using the eigenvalue equation, we get A square acting on ket lambda here is lambda square multiplying ket lambda. So we have lambda square. From here, we get a lambda star square because A dagger square acting on bra lambda will give you lambda star squared multiplying bra lambda. Okay, and from here we have 2A dagger A. So let's look at this term alone. Bra lambda 2A dagger A ket lambda. Again, we can use the eigenvalue equation. All right, so this is twice. Let me write it. Bra lambda, A dagger acting on bra lambda from the right. This is the 2 is there, and this is lambda star. Okay, and A acting on ket lambda is lambda multiplying ket lambda. And what is 2 lambda star lambda? It is 2 modulus of lambda squared. All right, so this term gives 2 modulus of lambda squared, and of course we have a 1 here. All right, now again we can use the normalization condition. Bra lambda ket lambda is 1, so we are left with h bar divided by 2 m omega lambda square plus lambda star square plus 2 modulus of lambda square plus 1. Please work out the steps of this calculation for a better understanding. We can now calculate the dispersion of the position operator, which is the expectation value of x square minus the square of the expectation value of x. We have calculated the expectation value of x squared. We have calculated the expectation value for x. Just put all that in here, simplify this, and we get the dispersion of x to be h bar divided by 2 m omega. Note that the lambda has disappeared. There is no lambda or lambda star in here. This is completely independent of the eigenvalue. This means that two coherent states corresponding to different eigenvalues of the annihilation operator will give the same dispersion for x. In the same way, we can calculate the expectation value of the momentum operator. I leave the steps as an exercise, and we get expectation value of P is equal to I square root of m h bar omega divided by 2 multiplying lambda star minus lambda. The expectation value of P square also can be calculated. The steps are very similar. Again, we have an A dagger here. We have to write it in terms of A dagger A. We can do that by using the commutation relations, just as in the previous case. Okay. And here we get the expression for the expectation value of P square. We can now calculate the dispersion of the momentum operator. The steps are simple, and we get mh bar omega divided by 2, again independent of lambda or lambda star. The product of uncertainties is now h bar divided by 2 m omega multiplying h bar m omega divided by 2, which gives h bar square divided by 4. Indeed, the product of uncertainties is at a minimum, because the generalized uncertainty relation says that this product has to be greater than or equal to h bar square divided by 4, and here the equality is satisfied. So the product of uncertainties is minimum in a coherent state. Now we already saw that under time evolution, a coherent state remains to be an eigenket of the annihilation operator. That is, if a state is coherent at t equal to 0, then it will remain so at any later time. Now, since dispersions of x and p do not depend on eigenvalue, the product of uncertainties also remain the same. Right? The product of uncertainties, because the dispersions of x and p are constant. They don't depend on the eigenvalue. Right? So they remain the same, which means that the product of uncertainties also will remain the same at a minimum at all times. We saw that the only thing happening to a coherent state under time evolution is that the eigenvalue of operator A changes. Alright, the state remains coherent, which means that the state remains an eigenket of operator A, but it's an eigenket of operator A with a different eigenvalue. But these dispersions do not depend on eigenvalues, so their products also will remain the same at a minimum h bar square divided by 4. In the language of wave functions, we can say that the coherent states remain a minimum uncertainty packet for all times. Now, among wave functions, only Gaussians have such minimum uncertainty products. So what we are saying is that the state remains a Gaussian for all times. We saw that delta x is a constant. This means that the uncertainty in position does not change. All right, the uncertainty does not increase or decrease. It remains the same. This means that the Gaussian does not change shape. All right, so all we have is a Gaussian. The wave function representing a coherent state is a Gaussian, and it just moves back and forth without changing its shape. All right, it does not spread out, it just retains its shape. So this wave packet actually behaves like a classical particle. Right, a classical particle just oscillates back and forth. And the behavior of this Gaussian is also similar. It just oscillates back and forth without spreading out. In this session, we had an introduction to coherent states. We just saw some of its important properties. I hope you followed the discussion. Thank you.